Okay, so major technical difficulties this morning. I recorded most of this and then realized the microphone had been turned off. So I get to do it again, so that's great. Apologize for the lateness at this point. But okay, so we have been talking about alkynes and the reactions of alkynes. And so just as a reminder, we have two different types of alkynes. We have what we call an internal alkyne, right? So this is where that carbon-carbon triple bond is in the middle of a molecule, right? So we call this guy internal. And then we have what is called a terminal alkyne. And a terminal alkyne, that carbon-carbon triple bond essentially terminates a molecule, right? So it ends a molecule. And so we're going to have that carbon-hydrogen bond on the outside. So this is what we call a terminal alkyne. Now, these last reactions we're going to go over are going to be dealing specifically with terminal alkynes because they're actually going to give us a means or I guess an important reaction synthetically that we haven't really talked about yet before, okay? So now, with respect to terminal alkynes, we talked really early on in this chapter about the acid-base properties of alkynes, right? The acidity of alkynes. And we had talked about how, kind of comparatively to other organic molecules, these terminal alkynes are actually fairly acidic, right? So they're not acidic in terms of like, oh, hydrochloric acid is acidic, but compared to other organic molecules, they are fairly acidic. So that proton can be deprotonated or can be taken off, removed, if you're using a strong base. And we talked about kind of the base that can do that is this guy, which is our amide ion, right? So this usually comes in the form of sodium amide, and I'm just going to go ahead and remind you what that amide ion looks like. So it's essentially just a deprotonated ammonia, pardon me. Again, this comes in the form of an anion. We can't just have that be by itself, right? It's never going to just go and be by itself. It's always going to have some sort of counter ion with it, and so that's where the sodium part comes from, right? It's essentially just the counter ion to the amide ion, okay? But the real player in this is the base, the sodium amide, and I'll go ahead and rewrite that. So, or the amide ion, this is our sodium of that sodium amide. Okay, so again, this is a strong enough base. It is strong enough to deprotonate our acetylene, right, in a proton transfer reaction, and the product of that is going to give us this alkynide ion, okay? So this is a deprotonated terminal alkyne, and again, we call this the alkynide ion. Now, there's a couple of things to note about this. So this reaction can occur, but specifically with respect to the alkynide ion, this alkynide ion, first off, is itself a very strong base, right? So carbon with a formal negative charge is not very stable. So if this is in the presence of something that it can deprotonate, it will deprotonate it, right? So it is a fairly strong base. On the other hand, I think, again, strong bases tend to go hand in hand with another property of this molecule, and that's the fact that with this formal negative charge, with this lone pair of electrons, this is also a very strong nucleophile. So this is also a very strong nucleophile. That's a pretty writing on this morning. So nucleophile. I'm so glad I wasted all of that time with the microphone turned off. Okay, so, well, that's great. So we can make this alkynide ion, right? We put our terminal alkyne in the presence of a really strong base like sodium amide. It forms this alkynide ion. We can then do lots of chemistry with this alkynide ion, right? So again, because this is a strong nucleophile, let's say that we had this. So we'll take our newly formed alkynide ion. Let's say we put this in the presence of some sort of nice, let's say, primary alkyl halide. So let's say that we put this in the presence of like an ethyl iodide, right? So again, I'm drawing the bond line structure of this guy. I've got ethyl, and it's attached to a nice halogen on the outside. So again, you guys should be able to see, well, this is an alkyl halide. It's a primary alkyl halide because, again, this carbon has bonds to only one other carbon here, right? So we've got our strong nucleophile over here in the alkynyde ion. We've got a nice primary alkyl halide. Hopefully you guys should be able to see that this is going to predictably undergo a substitution reaction, right? So we're going to bring back our nice SN2, where this guy attacks the alpha carbon, right? So remember alpha carbon, the leaving group, our iodide, our halogen is going to leave, and we're going to get, as a result, we've got our carbon, we're going to get the formation for the first time of a carbon-carbon bond. All right, so it's unfortunate that I've drawn kind of like a mixture of Lewis structures and bond line structures, but this reaction is taking a carbon and it's making a bond with another carbon. Right, so this is the first time that we have been able to make a carbon-carbon bond. Right, and so this is going to have some important ramifications synthetically, because essentially before this, we've only been able to say, okay, I've got a molecule, I can, let's say, move a pi bond. We can do that at this point in time, and I can move the position of a functional group. But this is going to essentially allow us, if we can make carbon-carbon bonds, to extend a carbon chain. So we can now extend a carbon chain, and we can add on carbons to a molecule. Okay, so a couple things to note here with respect to this. So notice how this was a primary alkyl halide. This reaction, this is called the alkylation reaction, so alkylation. This is going to only work with methyl and primary, so primary alkyl halides. This will not work with secondary or tertiary alkyl halides, and then the reason behind that is because this alkynide ion, it's a strong nucleophile, which is great, but again, as a reminder, it is also a strong base, right? And so when we have these molecules that are strong bases and strong nucleophiles, we have the competition between our bimolecular substitution reaction as well as our bimolecular elimination reaction, right? And so we talked about, so if it's methyl or primary, it usually undergoes this SN2 reaction, where if it's secondary or tertiary, then the elimination starts out-competing. We don't want the elimination product right here. We want this to be a substitution, and so that's only going to work for methyl and primary alkyl halides. And so, like synthetically, the way we would write this, so if I was going to write this reaction itself in like our synthetic arrows with reagents on the arrow, I would have my starting material here. I would then write number 1 as a first step, that we're going to take our terminal alkyne, we're going to react it with sodium amide, so that's our first step. Then in a second step, I would add the alkyl halide, whatever I'm trying to attach this to. So if we're up here, this was ethyl iodide, so we can either write that as the bond line structure of the molecule, or we could write that as ethyl iodide. And again, these are 2 sequential steps, so you do have to use number 1 for sodium amide, number 2 for ethyl iodide. You can't just say, oh, I'm throwing everything in a pot and it's going to work, because again, this is also a very strong base. It cannot be in the presence of this, or we're going to get a lot of side products that we don't want, right? So it's this guy reacting with this guy first. We take the product of that reaction, and then we will add it to this, and that will give us our overall new carbon-carbon bond, whatever we are trying to form. Separate these guys, right? So this is how we would write this synthetically. Okay, so other things, we can also use this with acetylene to kind of produce any type of molecule that we want, right? So for example, let's say that starting from just really base precursors, which is kind of the purpose of synthesis, you're starting from really just simple molecules and you're making very complex molecules. Let's say that I wanted to make something that looked like this, right? So I wanted to make this, and the only thing I had to start with was just plain old acetylene. So as a reminder, acetylene is this guy. This is acetylene. and it's just our basic carbon-carbon triple bond with no other type of carbon chains attached, another type of alkyl chains attached. Right? So it just has those two terminal alkyne, or two terminal protons. Right, so if we just started with acetylene and we wanted to make this, essentially all we had to do is undergo two separate alkylation reactions, right? So if we took acetylene and on one side of the molecule we wanted to add this. So this is 2 carbons. This is an ethyl group, right? Let me go ahead and write that. This is ethyl. On the other side, we wanted to add just 1 carbon. So on the other side, we wanted to add a methyl group. We could do that by undergoing 2 sequential alkylation reactions, right? So in the first step, we could add this to ethyl iodide, and then in the second step, we could add this to a methyl iodide. So this is going to be very helpful because now we can take little things like acetylene and we can make fairly complex molecules like this, which is a 1, 2, 3, 4, 5, a pentyne, a 2-pentyne. Now when we do this, we need to do this in different separate reactions, right? We can't just throw everything in the same pot. We can't just say, oh, I'm going to take acetylene, I'm going to add 2 equivalents of my strong base, and I'm going to add a bunch of different alkyl halides, and I'm going to get the actual material or the product that I want. Again, we can't do that because we're going to get a lot of separate side reactions, right? And a lot of stuff that we don't actually want to form. So when we do this, we need to do it in 2 separate steps where we add one side of the chain in the first step, and in the second step we'll add the second side or the other side of the chain. Okay, so what type of problems could you see that would deal with something like this? So let's say that you're given a problem which asks you to take acetylene and turn it into 7-methyl-3-octyne. Right, so anytime we're dealing with these type of word problems, the first step that you guys have to, go about in answering this is taking our name and turning it into a structure. And so octyne has 8 carbons in it. So if I go ahead and start drawing the product that I want to make, we've got 1, 2. Again, the ine starts at the 3 position. So 1, 2, 3, 4, 5, 6, 7, 8. That's ugly. 4, 5, 6, 7, 8, right? So if we get 1, 2, 3, 4, 5, 6, 7, 8. So we're good. We've got octyne. Again, that carbon-carbon triple bond starts at the 3 position. So we've got 1, 2, 3, 4, 5, 6, 7, 8. And the only thing we're missing at this point is this methyl group at the 7 position. Right? So this is what we want to make. And we want to make this starting from this guy. So this is the question that we're trying to answer here. What is going to take acetylene and what is going to make this 7-methyl-3-octyne? So now, to answer this, I'm going to divide my molecule up into what's on the left-hand side of the triple bond and what's on the right-hand side of the triple bond. So over here, the only thing we have to attach to this triple bond is a 1, 2 carbon chain, right? So 2 carbon chain is an ethyl. So that's what I need to attach over here. On this side, we've got a little bit bigger of a molecule, right? We've got a 1, 2, 3, 4, 5. So this guy overall is an isobutyl group, right? Again, isobutyl because we have that Y at the end. So what we're trying to attach over here looks something like this. Again, 1, 2, 3, 4, 5. Over here, it looks something like this, right? So isobutyl and ethyl, okay? So again, what this is going to come from is a deprotonated alkyne that is going to attack a primary or a methyl alkyl halide. And so whatever groups I'm wanting to attach, all I need to turn them into is that alkyl group with a halogen, right? So this guy would have derived from, or this side would have derived from this thing over here attacking an ethyl iodide. And then for this side, in a second step, we're going to have whatever the product is, we're going to deproton it, and it's then going to attack this, let's say, isobutyl iodide. Okay, so we'll say we're going to deal first with this step, and then we're going to go over and deal with this other side in the second reaction. Okay, so how would we go ahead and write this? So number one, we're going to take our acetylene, and in the first reaction, we're going to add that ethyl group to it. So to do that, our first step is to deprotonate it. So we'll add our sodium, actually, let's get closer to the arrow. We'll add our sodium amide. In a second step, we will then add this to our alkyl halide, right? So this is, we've deprotonated, we've made this really great strong nucleophile. We're then going to add it to our alkyl halide. We can write this as the bond line structure, or we can say ethyl iodide, however you want to write that. I like to write the bond line structure because I then don't get confused. And then really quickly, I want to move this up. Let me erase this guy. Go back to this thing being a thing here. Okay. So that's number one, or actually let's move this guy down. And erase, 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 erase. And then move this guy back up. Oops, not what I wanted. Sorry. Okay, so the product of this, again, is going to add that ethyl group to the left-hand side of our carbon-carbon triple bond. And so this is going to be the first product of this reaction, right? Okay, so now, again, we still have a nice terminal alkyne, right? We still have a proton there. We can still deprotonate it. So in the second step, we're going to do the exact same thing. So we're going to add this to our sodium amide. And this is going to get added. It's going to deprotonate it. That's going to be our first step. It's then going to attack our next primary alkyl halide. So I'm just going to go ahead and draw out the bond line structure for this guy. Wait, oh, I went down instead of up. I don't want to do that. I'll run out of space. So we have our iodide, down, 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 up. So again, just to make sure that I have not messed up my carbons here, I've got 1, 2, 3, 4, 5. Nope, of course I messed up my carbons. So second step is always to make sure that you get the right carbon, right number of carbons. So it's important to count carbons at this point in time. So we've got iodide is down here. So now we've got 1, 2, 3, 4, 5, and we are trying to add 1, 2, 3, 4, 5. Okay, so you can put that like that. For this one, since it is fairly simple, you could probably also write isobutyl and then iodide. I don't know, that may get confusing, so I would probably go with writing this guy. But again, gets deprotonated, right? It's going to attack this nice primary alkyl halide, and the product of this reaction will be our nice, happy, what are we making here? 7-methyl-3-octine, okay? So again, I want to make sure, just to be safe, to count carbons. So we've got our ethyl group, right? We've got the 2 carbons from our acetylene, and now we've got 1, 2, 3, 4, 5. And we had 1, 2, 3, 4, 5. Okay, so we started with 1 carbon, 2 carbon. We added 3, 4, and then we added 5, 6, 7, 8, 9. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we're good. Right, so again, this is the answer, right? This is one way that you could write this in 2 separate reactions. Long term, what we're going to do is start to kind of collect all of our synthesis stuff on the same like arrow up here. So another way that we could have written this is we have our starting material, which is this guy. We have our product over here, which is this guy, and then we're just going to list everything that's involved in this reaction in our individual steps. So first off, we had that sodium amide. We then added that to our ethyl iodide. In a third step, we took the product, we added it back to sodium amide, and then we added it to our isobutyl iodide. I need to get better at drawing because this is like the only way that we're going to be able to communicate. 1, 2, 3, 4, 5, yes. Ah, that irritates me, it's so ugly. Okay, so another way to do this is just to list everything above and below the error in the individual steps. You could also do it like this and be fine. Okay, so go ahead and try this on your own. So we're going to, again, start with acetylene. I want to know what reagents are needed to take that and to make 3-hexyne. So give this a shot, and then, or push pause on the video, give this a shot, and then come back and get the answers. Okay, so hopefully you guys actually did give this a shot. So we're taking acetylene. We can go and draw that out again. So acetylene is nice and easy. It's just 3 nice lines. And long term, we want to form 3-hexyne. So hexyne, we've got 6 carbons. It's an ine, so it starts the triple bond at the 3 position. So if we drew this out, we would get something that looks like this. 1, 2, let me make sure. We've got 1, 2, 3, 4, 5, 6. Okay, so again, 2 steps in this. First off, we're going to say, okay, what am I adding to this side? And then what am I adding to this side? And so over here, we're adding an ethyl group, right? So this is just a 1, 2 carbon ethyl group. Over here, we're also adding another ethyl group. So again, it's just a 1, 2 carbon, 1 and 2. So I've taken those apart, and so now if I want to add these guys have to be in the form of these primary alkyl halides. So all I need to do here is just add a halogen, right? So this is an ethyl iodide. Also over here is an ethyl iodide. Okay, so from there, we're just going to take our nice acetylene. We're going to react it first with our sodium amide to deprotonate it. We'll deal with the left-hand side first. So after it's deprotonated, we'll add it to our ethyl iodide, and we will get our first product, which looks like this, 1, 2, 3, 4. So that's a 1-butene. And then in a second reaction, we'll deal with the other side of the molecule. So again, now we need to add this guy. So to do that, we'll deprotonate our 1-butene. This is sodium amide, and we will add it to our alkyl halide that will produce the other side of the molecule. So that deprotonated alkanite ion will then react with our ethyl iodide again, 1, 2, and we will get, as a result, this guy, which is what we wanted. So again, you could have listed this as its bond line structure. You could have also said ethyl iodide or ethyl iodine or. And if we wanted to just write everything on one synthetic arrow, then we would write first off sodium amide, second off ethyl iodide, third we've got sodium amide again, and then fourth we've got our second ethyl iodide. Okay, so these are the reagents that would answer this question. And again, we can't just do this all in one go, right? We have to list these guys in separate steps. The numbers are trying to imply that we're doing separate reactions. We're working up the products, and then we're moving on to a second reaction, a third reaction, etc. Okay, so this is where I got when I realized the microphone was turned off. So here we are, back to where I originated from. Okay, so a couple of things to note. All right, so we're going to start trying in these next chapters, the chapters that we've been dealing with, trying to develop a kind of like a synthetic toolkit, right? So long term, we're building up to this idea behind synthesis. And in synthesis, what we're wanting to do, we're wanting to take these really simple precursor molecules, things like acetylene, things like, methyl iodide, ethyl iodide, and we want to build them up. We want to make pretty much any type of molecule that we could potentially ever want to make. That's kind of the purpose of synthesis. And so again, to build up to that, to be able to make things, we have to have these reactions, right? We need to know, okay, so, you know, if I've got this and I've got this, how are they going to react? What are they going to form, etc. And so we're kind of developing that toolkit at this point in time. So kind of to keep track of that, the book goes over a nice little brief review of things that we can do right now, right? So in this chapter with respect to alkynes, we've learned a couple of new reactions that we can now add to that toolkit. And specifically, one thing that we can talk about is the ability or the means by which we can move between an alkyne to an alkene to an alkane, right? So we talked at the very beginning of this chapter that if we have an alkyne and we want to fully reduce it to the alkane, we can do that, right? So we just need to take our alkyne, we need to react it in the presence of hydrogen and platinum metal as a catalyst. That will give us full reduction to the alkane. We also know how to go from an alkene to an alkane using the exact same hydrogen and platinum metal. And then we also have learned at this point in time how to take an alkyne, oh no, it's slow, how to take an alkyne and turn it into an alkene. So we have two different options depending on the alkene that we want. If we utilize hydrogen in the presence of a poison catalyst, hopefully you guys will see which alkene will that give us. That will give us the cis alkene, right? And if instead we use the sodium metal in liquid ammonia, so this was our dissolving metal reaction, this would give us our trans alkene. Right, so depending on what type of stereochemical outcome we want, depends on the actual reagents that we're going to utilize. So we have two options here. Okay, so now we can do this, right? We can take alkyne, we can go to alkene, we can go to alkane, or vice versa. Now the question is, can we do the reverse, right? So first off, can we take an alkane and can we make an alkene with it? This is a big question, right? So can we synthetically do that? Second, can we take an alkane, can we make an alkyne? Or more importantly, can we take an alkene and make an alkyne, right? So this answer is yes, but it's a qualified yes in the fact that we don't know the reactions yet. We will be able to in the next chapter. So we're going to put this one on pause. We'll come back to this question here. Can we take an alkane and make an alkene? But we can, or we should, at this point, kind of have a means to do this, to take an alkene and make an alkyne, right? So we learned at the beginning of this chapter how to make an alkyne, right? We needed to undergo an elimination reaction, right? And it was a very specific 2 times elimination reaction. And that was going to essentially result or come from a dihalide, right? So we needed a dihalide, and then we needed that to undergo 2 sequential eliminations to produce our alkyne. And so the question is, well, can we take an alkene and make this dihalide? And ideally you should be able to see, well, yes, right? We can take an alkene, we can have it undergo that bromination reaction, right? Where bromine adds in an anti-fashion to our alkenes. So this is our addition reactions. We can then take that and undergo these 2 sequential eliminations to get our alkyne, right? So we do have a means by which we can take an alkene and produce an alkyne. And again, that's going to undergo, we're going to have our halogenation reaction, our bromine, in the presence of a non-nucleophilic solvent. That's important. Because again, remember what happens if this is in the presence of a nucleophile or a nucleophilic solvent. We won't get our dihalide as a product. We instead get our halohydrin or whatever type of nucleophile we're looking at. So bromine in the presence of non-nucleophilic solvent, something like carbon tetrachloride, will give us our dihalide as a product. That dihalide, at this point, that dihalide is vicinal. But that vicinal dihalide can then undergo this double elimination. So to do that, we used excess sodium amide. And then in the second step, to make sure that we end up with our protonated end result, protonated alkyne, we had to add water in a second step, right? Because again, this excess sodium amide, it's going to undergo, or it's going to have our dihalide undergo that double elimination reaction, but then it's also, what we just learned, is going to deprotonate that final alkyne, right? So we don't want to end up with the alkanide ion. To ensure that in a second step, that's why we add water at the end here, to ensure that we end up with our protonated, non-deprotonated alkyne. Okay, so we can do this. We can take an alkene to form an alkyne. It just has two different reactions. So this is reaction number 1, and then reaction number 2. Again, to take an alkane and turn it into an alkene, we can also do this. We don't know how to take an alkane and produce a functional group in it. We will learn this in this should be 10 in our radical chapter. But if this was, let's say, a bromine, which it will be long term, if we have an alkyl halide, we do know how to produce an alkene. We can use a strong base here and undergo, again, an elimination reaction. And we'll talk about that more once we can actually produce this from an alkane. Okay, so now we're going to do kind of like a practice problem with respect to getting into this synthesis mode, this idea of taking these precursors, these simple precursors, and making whatever we want with them, right? So in this problem, they're asking us to propose an efficient synthesis. So they want to know the reagents and the order in which we're going to add them to take our starting molecule here, so this guy, and we want to make this guy out of it. Okay, so the first step in doing this is kind of, I guess, grounding ourselves. What can we do? What can we not do? At this point in time, we do know how to move a pi bond, so we can move the position of a pi bond. So that's number 1. We can move a pi bond. Number 2, we can also move a functional group. Please stop. And now another thing that we've learned how to do at this point is we can extend a carbon chain. So we can make a carbon-carbon bond. So then the question is, well, what's kind of happened, right? So we started out here with our cyclohexane ring, right? So we had cyclohexane. Let me get rid of this guy. I don't like that. So we had cyclohexane, right? And then attached to it, we had a 1,2 carbon group. Over here in our product, we still have that cyclohexane. We have a 1,2,3 carbon group now, right? So we can note that it does have a functional group in it. It has a pi bond, and that pi bond is at this 1,2 position. That pi bond has not changed positions in our product, right? So we end up with the same pi bond, same position. So we don't need to really worry about moving it. We don't really need to worry about moving functional groups, right? Because there are no functional groups. The only thing that's really happened here is this is extended a carbon chain, right? We've added 1 carbon, a methyl group, to what we initially had. So then the question is, well, how can we extend a carbon chain, right? What do we need to do that? And the answer to that is, well, the only way we can do this is if we have a terminal alkyne, right? If we have a terminal alkyne, then we can deprotonate it, right? And then we can add it to whatever we're trying to add it to, or whatever we're trying to extend it to. We can add it to that methyl iodide or ethyl iodide, or whatever we're trying to actually produce, okay? So that's going to be the way we go about this, right? Number 1, we need to extend this carbon chain. The only way we can do that is if we have a carbon-carbon triple bond. So my first question is, how do I take my starting material, and how do I make a carbon-carbon triple bond at the end of this molecule? How do I turn this guy into this guy? Right, so this is our big first question. Once I'm here, right, once I've turned my double bond into a triple bond, then the question is, how do I take that triple bond? How do I make it add a carbon? Right? The only way that we can do that, there must be a way that we can extend that. And then the last question is, how do I take this carbon-carbon triple bond this monstrosity that we've created, and how do I turn that back in to very specifically a very specific alkene. Okay, so for me, this undergoes 3 different types of processes here. How can I take this guy and make this guy? How can I add a carbon to that guy? And then how can I turn that alkyne into an alkene? Okay, so first off, how do we do this, right? How do we take an alkene, which is what we just mentioned? How do we take an alkene? How do we make an alkyne? And the answer to that was what we had just kind of reviewed, was the fact that, well, we can take this alkene and we can have it undergo that bromination reaction, that halogenation reaction, right? So number 1, we can have this guy in the presence of bromine dibromide, the dihalide, in a non-nucleophilic solvent like carbon tetrachloride. I'm going to ignore the cyclohexane part because I don't want to draw that over and over again. That's going to give us our vicinal dihalide, right, when we add bromine to this guy. We can then take this guy and we can have it undergo that double elimination followed by protonation to end up with that alkyne, right? So this was the excess sodium amide in the presence of water in a third reaction, right? So number 1, we have our bromination followed by our elimination, excess sodium amide, and then in the third step we're going to have water. That will take our alkene, that will turn it into our alkyne. Okay, so that's the first real step here. Number 2, how do we take an alkyne, or this alkyne, our terminal alkyne that we've just made, and how do we add a carbon? Right, that's all we really want to add to it, is just this guy. So we know how to do that, right? We can say, okay, first off, I'm going to deprotonate this alkyne, right? So to do that, I need my sodium amide again. And then in a substitution reaction, I'm going to add this deprotonated alkyne to whatever I'm trying to have it attack, right? And so all we need is a methyl group, right? So this can be just your methyl iodide, or you could just write methyl, not that, or you can just say MEI, methyl iodide. So the first step in this is going to deprotonate this guy. It's then going to attack our methyl iodide, and we will end up, so this guy is, number 2 is methyl iodide, and we will end up with our, great, that's great. We'll end up with our new extended carbon chain, right? So this would be the product of that reaction. Now the question is, okay, we don't want to end up with the alkyne, we want to turn this back into an alkene. So then the second question is, what type of alkene, right? Because we have a couple options here. To reduce an alkyne to an alkene, we have our poison catalyst method, and then we also have our dissolving metal reduction method, right? And so the question is, well, what type of alkene are we trying to produce? And so the answer to that depends on the stereochemistry, right? This specifically is a transalkene. This is not the cisalkene. So to take an alkyne and make our transalkene, that is only one reaction specifically, and that is our dissolving metal. So then for this guy, it would be sodium metal in the presence of liquid ammonia. And that is it. That is how we take this molecule as our starting material, and that is how we produce this molecule overall. Okay, so again, it was how many different steps? We had one separate step. All right, so this had 3 different reactions involved in it, taking our alkene, making an alkyne. We had that alkylation reaction in our second step to add to our carbon chain. And then in the third step, we had to reduce that alkyne, and we had to produce our transalkene, and so that was the dissolving metal reaction. So you can do this again the way I've listed it. You can also collect them all over the arrow, and again, they have to be written in the order in which they are performed. So the first step was our bromination reaction. This was then followed by our elimination, so excess sodium amide. third step in that was water to protonate and get our protonated alkyne. In a fourth step, we had to go over here. We had sodium amide again. And then we had to add that to our methyl iodide. And then finally, in a sixth step, final step, we had our internal alkyne. We needed to reduce that to our transalkene. And so we utilized our sodium in the presence of liquid ammonia. So there's not a lot of room there. I should have maybe expanded that a little bit more. But again, that's how you go about answering these synthesis problems. So first off, number one, what have we done, right? Have we moved a functional group? Have we moved a pi bond? Or have we extended the carbon chain? And so then the question is, okay, well, we only have one means by which we can extend a carbon chain, and that depends very heavily on the fact that we need an alkyne. So how do we get from whatever we're starting at to the alkyne? How do we extend the chain? And then how do we get back to whatever we're dealing with at the end? Okay, so I want you guys to give this one a go. These guys are kind of similar to what we've seen. They're going to have some different end results. I'm going to extend this or maybe move this to, I don't know, a different slide. There's not a lot of room here. But go ahead and push pause on this. I've got 3 different problems that I want you to propose a synthesis for. And so go ahead and give these a shot and then come back to the answers. Okay, so I'm going to start with A up here. And so I'm going to go ahead and just grab this guy and move it over here. Oh, I don't want to do that. Nope, don't want to do that. Let's move this guy, and then we'll move this guy a little bit over here. Okay, so a couple things to start with, right? So obviously on this first one, it's very similar to what we just saw in the practice one. So we have 4 carbons to start with on our starting material, and if we move over to our product that we're wanting to synthesize, we've got 1, 2, 3, 4, 5, 6 carbons, right? So we have extended our carbon chain. So we know there's only one reaction we really know how to do with respect to that, and so we're probably going to need to deal with that alkylation reaction at some point in time. Right, so this is a very similar one, right? We start with a alkene. So we start with an alkene, and we know this is probably going to have to go into an alkyne at some point in time because, again, we need a terminal alkyne to undergo that alkylation reaction so that we can actually extend the chain, okay? So we're going to probably need to take our alkene. We're probably going to need to make it an alkyne. Right, so we had 4 carbons initially. We have 1, 2, 3, 4, and our proposed alkyne. With that alkyne, we need to extend it, or we need to extend our carbon chain 2 carbons, right? So we probably need to take that alkyne and somehow turn it in to something that looks like this, right? Because we have 6 carbons now. So this is what we have originally. We're going to need to add this, and then somehow we're going to need to take that alkyne and turn it back into an alkene, right? So we have an alkene. We need to make an alkyne with it. We need to add 2 carbons to that alkyne, and then we long-term need to somehow take that alkyne and turn it back into an alkene. Okay, so how do we do that? Right? We've already talked about how we can take an alkene and make an alkyne. That's going to be that, first off, that halogenation, that bromination reaction. So bromine in a non-nucleophilic solvent. That's going to take our alkene. It's going to add to it, right? So that we now get our dihalide. We're then going to take that dihalide and we're going to undergo that elimination reaction, right, with that strong base. So we've got excess sodium amide. Again, if we had just left it there, what we would be left with, because that sodium amide can deprotonate these terminal alkenes, is we would be left with this alkanite ion, right, which is not what we want. And so we have to add in water, which is a strong enough acid to protonate this so that we do end up with our protonated alkyne as a result. So we've got bromine carbon tetrachloride. That's going to form our dihalide. Then we're going to take that dihalide. We're going to undergo 2 successive elimination to produce our alkyne. Now, once we're at the stage of this alkyne, we're going to need to, again, deprotonate it with that sodium amide. And now we're going to need to add it to whatever we need to extend the chain with in terms of an alkyl halide, right? So we need to add on 2 carbons. We need to add on an ethyl group, right? So we're going to have that deprotonated alkyne act as a nucleophile on this, our ethyl iodide. So this is going to be this guy with ethyl iodide. That's going to give us our alkyne. We have that, again, triple bond at the 3-4 position. In our end product, we need that alkyne to be an alkene. We need a double bond instead of that 3-4 position. But most importantly, and this is the big difference, because we do have reactions that will take an alkyne and make an alkene, we need this specifically to be the cis alkene, right? So there are 2 reactions that are going to take an alkyne to make an alkene. Only one of them is going to produce the cis alkene, and that one specifically is that hydrogen in the presence of a poison catalyst, which we use Lindlar's catalyst as our poison catalyst. Lindlar's catalyst. Let me see if I can spell that. Catalyst. Okay, so that's a bunch of different things, right? So I'm going to go ahead and write above our little arrow here. I'm going to use black. So the first step was taking an alkene and making an alkyne. That was bromine, first off, in the presence of a non-nucleophilic solvent. So we've got carbon tetrachloride. Number 2, once we form our dihalide, we then need to have it undergo excess sodium amide to undergo that sequential double elimination. Then we need to add water to make sure our product is protonated. In a 4th step, we will deprotonate it again. So that's sodium amide. Now we have our alkyne. We're going to deprotonate it and have it act as a nucleophile in our alkylation reaction. And then finally, we end up with our 6-carbon alkyne. To make that our cis alkene, we need hydrogen and then Lindlar's catalyst. So Lindlar's catalyst. Okay, and so those are the reagents needed for this synthesis. Okay, so that's number 1. I'm going to go ahead and take number 2. Again, if you haven't worked on number 2, give it a shot, and then come back, pause the video, come back, and we will go over number 2. If you have, then go ahead and keep playing, and we'll go on, and we'll talk about how we're going to deal with this one. Okay. So first thing to note here is that we don't have an extension of a chain, right? So we have 1, 2, 3, 4 carbons. Over here in our product, we have 1, 2, 3, 4 carbons. So we don't have to undergo that alkylation reaction. So we don't need to worry about dealing with that. So that's nice, right? The problem is at this point, though, is that we have a triple bond that essentially just turns into an alcohol, right? A carbon-carbon single bonds, no triple bonds, no double bonds, and an alcohol instead, okay? And so one thing that could have happened in this is we could have had maybe a double bond here, right? So we could have taken this guy and formed a carbon-carbon double bond at that position. We could then take that double bond and undergo a hydration reaction to get our alcohol, right? Because if we hydrated that double bond, then it would be an H and an OH adding, and so that would give us our alcohol. So then the question is, okay, well, how do I take an alkyne, and make an alkene? So again, it depends on whether or not we want the cis or the trans alkene. That actually doesn't matter here because this is a terminal alkyne. So because there are 2 hydrogens here in the product, there is no cis-trans isomerism, right? So we'll go ahead and use maybe that dissolving metal reduction. You could also use hydrogen in Lindlar's catalyst. So dissolving metal would take our alkyne and turn it into an alkene. And now that we're at the stage of an alkene, to hydrate it, we have a couple of options. Again, it depends on whether or not we want the Markovnikov versus the anti-Markovnikov product. So Mark versus anti. Again, in Markovnikov, we have the OH adding to the more substituted position, which is what we see here, right? This position is more substituted than this position. So we do want the Markovnikov product. Again, just to avoid the possibility of rearrangement, we're probably going to want to utilize that oxymercuration, demercuration reaction, right? So this guy would be mercuric acetate, OAC2, in the presence of water. And then to remove that mercury, we're going to use the sodium borohydride. So note how I just kind of like pulled that out, right? I had an alkene, I wanted to make an alcohol, I wanted to hydrate it. Again, that's why I really stress those reactions that we're learning, or we're going to continuously learn, especially in terms of synthesis. So even though we've moved on past the addition reactions, we're still going to use them throughout, right? So it's important that you know them at this point in time. So okay, I think that's it, right? We have 4 carbons. We don't have to worry about extending the chain. So the only thing we need to do is take an alkyne and make an alkene, and then we need to hydrate that alkene in a Markovnikov fashion. So in our first step, we'll use that reducing dissolving metal reduction. Hold on. Sorry if that's loud. We'll use that dissolving metal reduction, so sodium in the presence of liquid ammonia. Once we have our alkene, then to hydrate it, all we need to do is use our oxymercuration. You could technically use acid catalyzed hydration, but I would just to be sure that you don't have to worry about rearrangement, I would always just use your oxymercuration, demercuration, because it'll give you the Markovnikov product and we won't see any type of rearrangement. Okay, so that's it. It's only 3 steps for this one. So now we'll do C. Again, if you haven't done C yet, go ahead and give it a shot. Pause the video, and then we'll go over this one. Okay, so I'm worried that we're going to get blown out with the noises outside. 1, 2, 3, 4, 5, 6. Okay, so a couple things to note. For this one, all right, we've got 4 carbons on our reactants or on our starting material. We've got 6 carbons in our product, so we are definitely going to have to extend the carbon chain. What's nice about this is that we start with an alkyne, so I would suggest doing that immediately, right? Taking our 4 carbon alkyne and turning it into a 6 carbon alkyne, right? So how do we do that? That's kind of the big question, right? So how do we take 4 carbons with an alkyne? How do we turn it into 6 carbons with an alkyne? And so hopefully you guys will say, oh, well, I know how to do that. The first step is that alkylation reaction. So that first step is going to be to deprotonate this, right? So number 1, we'll have our sodium amide. It will deprotonate our terminal alkyne, because that's what we have. This guy will then attack whatever we're trying to add on the other side, right? So this is, we're trying to add 2 carbons or an ethyl group. So this will be an ethyl iodide. So we'll add that guy. So we've got ethyl iodide. That is the reaction. So we'll have that first step, sodium amide. It will deprotonate that. This guy will then attack our ethyl iodide in an SN2 type reaction, and that will extend our carbon chain to 6 carbons, okay? So now we will be at the point that we are here. We've got 1, 2, 3, 4, 5, 6. So now the question is, well, how do we go from our 6 carbon alkyne to this dihalide, right? And so there are a couple of reactions that we learned with respect to the alkynes. We could undergo some sort of bromination, right? So we could have had this guy react. The problem is with that is that we would end up with either an alkene dihalide, so an alkene with 2 halogens on it, right? Or we would end up with the tetrahalide, right? So we could have done excess or 2 equivalents of bromine in the presence of this guy, and we would end up with a tetrahalide, which is not what we want. Instead, what we end up with is, you know, an alkane, and then we have 2 bromines, and those bromines are very specifically in the anti-position with respect to one another, right? We have 1 bromine on one side of the chain, we have the other bromine on the other. So these guys have added in an anti-stereochemistry here. And so the only real way we know how to do that is by having, first off, this specific alkene, right? So we know how to take this guy and add bromine in an anti-fashion, right? That was just that halogenation reaction, that bromination. So carbon or bromine in the presence of a non-nucleophilic solvent, it formed that bromonium ion, and so we got the production of the anti-product, right? So now the question is, well, how do I get from this to this? And again, how do we go from an alkyne to an alkene? Well, we have a couple options. Specifically for this one, we have the trans alkene, and so to produce an alkyne from the trans alkene, we're again going to use that dissolving metal reduction. And so I think that pieces together all of the parts, right? So we have our alkyne. We're going to elongate. It's a terminal alkyne, so we're immediately going to elongate our carbon chain by undergoing this alkylation reaction. Alkylation. We're then going to take our 6-carbon alkyne. We're going to produce our 6-carbon alkene, specifically the transalkene. And then once we are at the point of that alkene, to get to our final product, all we need to do is have it undergo that bromination, that addition reaction, which again is something that we learned in a previous chapter that we will utilize throughout. So if we added everything above the arrow here, oh boy, kids are out now. So if we added everything above the arrow, we've got first off alkylation, so sodium amide. Second step, we're adding it to our ethyl iodide to extend the chain. Third step, we've got our dissolving metal reduction, so sodium in the presence of liquid ammonia. Finally, in our 4th step, we're going to take our transalkene and we're going to halogenate it in an anti-fashion, that is our bromine in the presence of a non-nucleophilic solvent. So 4 different steps to this guy. Okay, so that was a lot, so go ahead and try to digest that. I would start getting to work on the problems for Chapter 9. This is the completion of all of the alkyne information that we're going to learn. We'll move on to Chapter 10, and I'll start working on those videos at this point. So do the homework, answer the quizzes, please, on Canvas. There's 2 different sites that we have to go to now. I apologize for that. We've got Wiley Plus for the homework, and then we've got Canvas just to ensure that you guys are watching these and that we're keeping up to date. So I know it's, especially with respect to these online type things, we can be like, oh, I'll watch it later, it's not due, and then we wait until the very last minute, and then we're struggling to watch the videos in time. So make sure you guys are keeping up to date with this so that you don't let it build up on you.